Next, we're going to talk about the central limit theorem, result, and meaning. Okay, so loosely speaking, the weak law of large numbers tells us that the difference between the sample mean and the true mean, mu, is very small or negligible. A little bit more formally speaking, the sample mean minus mu goes to 0 as n goes to infinity. Of course, this should be described in a more formal manner using the convergence in probability, but loosely speaking, this is true. However, we don't know how the mn minus mu converges to 0. What do you mean by how? For example, what is the speed of the convergence? For example, if this mn minus mu is equal to the order of 1 over n, the speed of going to 0 is the n goes to infinity is 1 over n. Or it's possible that, for example, 1 over square root of n, or maybe 1 over n to the 2 over 3, right? 1 over n, or 1 over square root n, or 1 over n to the 2 over 3 will have a different speed of the convergence. That's what we mean by the how mn minus mu converges to 0. Okay. So question is this, okay? Since the mn minus mu goes to 0, then if we multiply this by something, okay, and we want to make the scenario where n goes infinity, this multiplication goes to some meaningful thing, some constant, some value. Since this goes to 0, then this something should go to the infinity in order to make a balance between this something and mn minus mu, right? So this something should blow up, right? Now, what is this something, okay? One may conjecture that this something is some polynomial function of n, let's say n to the alpha. Now, the question is, what is the value of the alpha such that this product goes to some meaningful thing? Essentially, I'm asking the question that's, what's the speed of the convergence of mn minus mu? That's the question, right? So the question is, what's the alpha for our magic? That this product of the n to the alpha and the mn minus mu goes to meaningful thing? We can imagine the alpha is something, and the answer is alpha is 1 over 2. So this is the square root of root n. Okay. Now we need to understand why is that and what's the meaning of this result. Okay. So let's reshaping the equation. So we have an mn minus mu, and we're gonna multiply the square root of n by this mn minus mu. And for the beauty of the equation, we just want to multiply some constant, sigma here in this case. So sigma is not very, very important, just for the beauty of the appearance of the equation. But the important part is the square root of n. Okay. Now, the square root of n, and we have a sigma here. And by definition, the sample mean is Sn over n. So this becomes the Sn minus n mu divided by sigma n, and we have a square root of n here. Okay. Now square root of n, and this becomes the square root of n. So we have this Sn minus n mu divided by the sigma square root of n. Okay. Now let us denote this by Zn. Okay. Now let's compute the expectation and the variance of the Zn. Now you can easily see that the Zn has the 0 mean because the Sn has the expectation of n mu. So we have centered the random variable Sn by n mu. So that's why the expectation of Zn is 0. And the variance of the Zn is equal to 1 because the is equal to the multiplicator term. Okay. This does not make an impact on the variance. So this one. And Sn is equal to the x1 plus xn. And we know that the xi's are independent, so it's just a summation of the variance x1 and variance x2 and so on. So and multiplied by the variance of xi. Okay, so that's why this is cancelled. Sorry, this is cancelled, and 1 over sigma square and the sigma square. That's why this is 1. All right. So expectation is 0 and the variance of 1. Essentially, we have beautifully standardized this mn minus mu by multiplying the square root of n and divided by sigma and make Zn, and then we have beautifully standardized. All right. So Gn is well-centered with the variance irrespective of n. Okay. So whatever the n value is, the variance is 1, which is again the constant, and the expectation is 0. So we expect that Zn converges to something meaningful as n goes infinity, right? Why is that again? Because the expectation is 0 and the variance is maintained as constant. Essentially by multiplying the square root of n to the mn minus mu. Okay? So that's this square root of n plays a central role to make this product meaningful. All right. Now the question is that, okay, we expect that Gn converges to something meaningful, but the question is to what? Some deterministic number, just like the weak lobe large numbers, let's say some constant, which we don't know yet. The answer is that interestingly, it converges some random variable which we know very well. Okay, so Zn converges to some random variable z, which we know very well. But when we want to talk about the Zn converges to z, we have established the convergence for the sequence of the random variable, and that was the convergence in probability. But unfortunately, we will not prove that the convergence in probability for this case. In this case, we will develop a new concept of the convergence that is called the convergence in distributions in order to establish this result mathematically. All right. So let's study what is the convergence in distribution. Let's consider a sequence of the random variable yn, y1, y2, y3, y10, y100, and so on, and another random variable y. Okay, so I will define the convergence in the distribution, which we denote by this. Yn converges to some other random variable y in distributions if for every y value, small y value, the probability that the yn is less than or equal to y, and which is what? Some real number, right? Because it's a probability. That goes to some probability that this y is less than or equal to y, which is, let's say, a. Okay, so this an converges to a, then we say that the yn converges to y in distribution. So if you look at this probability, it's quite familiar to us, right? What is that? That's the CDF of yn, and this is the CDF of y. So the convergence in distribution is essentially corresponds to the convergence of the CDF. We have a sequence of the CDFs of the random variable yn, CDF of y1, CDF of y2, and so on. Okay, so we use this notation, right? Okay, that converges to the CDF of y. Okay, in that case, we say that the convergence in distribution. So it's kind of easy to understand, okay? So this convergence in distribution is another type of the convergence of the random variables. We have discussed the convergence in probability, and this is another type. And you might be wondering about what's the difference between the convergence in probability and convergence in distribution. So the comparison between those two concepts are interesting to ask. If I give you the answer, the convergence in probability implies the convergence distribution. Okay. If a sequence of the random variables satisfy the convergence in probability, that immediately implies the convergence in distributions, but the reverse is not true. How can we prove that? Well, the proof is beyond what this class covers, so I will skip that. Just we can accept that as a fact. But it will be interesting to find an example that shows the convergence in distribution, which is not the convergence in probability. Okay, meaning that this is not true. Okay. It's a very simple example. Suppose that the random variable xn is a Bernoulli random variable with the success probability 1/2. And that's for all n. So the x1 and x2 and x3, there, those are all same random variable, same Bernoulli random variable with the parameter 1/2. Okay? Okay? So x1, x2, xn. Okay? They're all same. Now I'm going to define a random variable x, which is the 1 minus xn. Okay? Now you can easily see that this random variable x also is a Bernoulli random variable with parameter 1/2. Okay? Why is that? Because the xn is equal to 2 with probability 1/2. And when the x1n is equal to 1, then the x is 0 with probability 1/2. And xn becomes 0 with probability 1/2. And in this case, x becomes 1. Okay, so the x is the Bernoulli random variable which has the same distribution as xn. X and x have the same distribution. It is trivial that the xn converges to x in distribution because their distributions are same. Okay? But what about the convergence in probability? So if you remember how to prove the convergence in probability, for any given epsilon, we need to prove that the probability that the difference between the x and x is greater than or equal to epsilon, that should go to 0 as n goes to infinity. That's how we prove that. Okay? Now, if you want to disprove this convergence in probability, then we need to find an epsilon such that it does not converge to 0. Okay? So let's look at that. So xn minus x greater than or equal to epsilon, the probability. And by definition, x is 1 minus xn. So this is xn minus 1 plus xn. And that is 2xn minus 1. Okay? So probability that the 2xn minus 1, the absolute value, is greater than or equal to the epsilon. But the 2xn minus 1 is always 1. Why is that? Because the xn is 0 or 1. When the xn is 0, then it becomes minus 1 and the absolute value is 1. And when the xn is 1, then this becomes 1, so absolute value 1 is 1. So absolute value of the 2x minus 1 is always 1. So that is equal to the probability that the 1 is larger than epsilon. Okay. Now we can find the epsilon small enough, let's say 0.9, so that this probability is always equal to 1. That does not obviously go to the 0 as n goes to infinity. Okay, so we disproved that the convergence and probability. So convergence and probability is not satisfied for this case, but convergence and distribution holds. Okay, so let's go back to the central limit theorem. So far, we have talked about the convergence and distribution concept. Then we're going to use those concepts in order to talk about the central limit theorem. So what is the central limit theorem? The summation of the random variable from xn1 to the xn, that's Sn. And we're going to define the Zn, which is equal to the Sn minus n mu divided by sigma square root of n. And it turns out that this Zn is the sequence of the random variable, Z1, Z2, and Zn, okay? This sequence of the random variable converges to some random variable Z in distribution, where this random variable is a standard normal random variable, which we know very well. Okay? That's the central limit theorem. Zn converges to a standard normal random variable, where the Zn is this, in distribution. This is a very surprising result. That's why people say that central limit theorem is one of the most remarkable findings in probability theory. Why is that? Because this result does not depend on the distribution of xi. Whatever the distribution of xi is, the limit random variable distribution is normal. Then you might be wondering, what is so special about this normal? Yeah, normal is that special. Okay? That's why the central limit theorem is very surprising and useful, as we will see later. All right? So let's make some comparison between the law of large numbers and central limit theorem from the perspective of the different scaling classes. Okay, so in order to simplify the discussion, let's assume that the expectation of xi and the is 0 and the variance of xi is equal to 1. Okay, we're talking about this thing. And each of these random variables mean is 0 and the variance is equal to 1. Well, otherwise we can center the random variable, as well as we can divide each random variable by sigma. Then well, essentially we can make this situation. So okay, what is the law of large numbers? Law of large numbers is that we're gonna scaling Sn by 1 over n, which means that this. So I have a new glasses, and then look at the Sn, but this glasses is a scaling by 1 over n. Then what you see is deterministic value. That's the expectation of xi, which is equal to 1 in this case. That's my new glasses. What about the central limit theorem? I change my glasses and look at this Sn and scale by 1 over square root of n. Okay, so essentially I'm looking at this. Okay, and we're gonna look at this Sn for large n, scale by 1 over square root of n. Sn is already well centered and standardized, so because we have assumed this thing. And then different from the law of large numbers, you will stay at the random one. You see the random phenomenon even with this new classes. But this random thing is not arbitrarily random. It's a normal random word. That's the new classes. That's the scaling by the 1 over square root of n classes. And not depending on the distribution of each xi. So whatever the distribution of xi is, if I take my classes, which is a scaling by 1 over square root of n, then I see the normal random word. If I change my new classes with the scaling of 1 over n, I see a deterministic word, just a one number. That's what I mean by the new classes, new scaling classes. So intuitively, lower large numbers and central limit theorem mean this: deterministic world or normal random world. Then, how can we use this central limit theorem in a practical situation? Okay, so the Zn is a kind of a standardized transformation of Sn. Now we know that the Zn will follow the Gaussian distribution, normal distribution for large n. Okay, so if people are wondering about the CDF of the Zn, and when the n is large, then we can approximate this distribution with the distribution of standard normal. That's how the CLT is used in practical situation. Okay, as I mentioned before, we can approximate the distribution of the Zn with the standard normal random variable if n is large. Okay, that also means that Sn is the n mu plus the Zn sigma square root of n. Then the Zn follows the standard normal random variable. That also means that the Sn follows the normal random variable whose mean is n mu and the variance is n sigma square. The reason is that if this is the standard normal random variable, if you remember, linear transformation preserves the normality, right? Where the a and b are the constant. So this is again the normal, where the mean of this normal is the a, which is n mu here. The variance is the b square of the variance of z, where the variance of z is a standard normal, so it's 1. So it's b squared. The b square is the b is a sigma square root of n, so it's the sigma square n. Okay, so that's what we mean by the Sn follows the normal random variable n mu and n sigma. That has the same meaning as the Zn follows the standard normal. Okay, all right. Now the question is that, okay, in order to have an exact approximation, it's not an exact approximation, it's like good approximation. How large should n be? Maybe 10 or 20 or 100? Well, it depends on the situation. By situation, I mean that depending on the distribution of original one is xi. So depending on the distribution of the xi, it will make an impact on the form of the Sn, and that will make an impact on the necessary n to have a very good approximation. Okay, typically a moderate n like 20 or 30 usually works, which is the power of the central limit theorem. But if xi, the distribution of xi, resembles the normal more, then obviously we just need the smaller n. So what I mean by the resemble more is that since the normal random variables PDF has the following form, distribution of xi is symmetric and also unimodality. Unimodality means that it has only unique mode, meaning that we have a single maximum or the minimum, something like this. Yeah, not this. Okay, so that's a unimodal. So if the distribution of xi is symmetric and unimodal, it resembles more the normal random variable, in which case we just need the small n. So let's look at the example. These are the distribution of xi, because that's the distribution of n is equal to 1. Now if you look at these two distributions, then obviously this distribution is symmetric, right? It's very uniform in some sense. But here in this case, it's asymmetric. Like we have large values for this case, and it go down and the small values. It's not. It's asymmetric. All right. So in this case, we need large n in order to resemble the normal random variable for large n. So here in this case, from the for example, like n is 16, we see a roughly normal random variable. For this case, even for n is equal to 4, we can see a approximate normal, and n is equal to 32, then we see almost exact like normal random variable. Now let's apply the central limit theorem to a practical problem. Okay, so the situation where we can apply the central limit theorem is this. We would like to know about the distribution of Sn. So by distribution means that, for example, like CDF, okay? So it has the following form, like the probability that the Sn is less than something is roughly the B. Okay, so B is the probability of the Sn is less than A. So in this case, we have three parameters like N and A and B. N is how many random variables are we going to take a summation of, and the A is the value of Sn can reach, and the B is the probability of the CDF of Sn. Okay, so we can ask the question that give two parameters like A and N, and we want to find the third parameter like B, for example. Or maybe we can give the two parameters like A and B. Then we are asking the question of N. So we're going to look at the three examples, each of which can correspond to give two parameters and find the third parameter. Okay, let's look at the case where N and A are given, and we would like to know the B. Okay, so suppose that we have a package, and the package weights are modeled by the random variable xi. That's the package weight of the package I, and that follows the exponential distribution with parameter lambda, where the lambda is 1/2. Then from the formula of the expectation and the variance, exponential random variable, the expectation is 1/mu, if you remember, and that is 2 because lambda is 1/2, and the variance of the exponential random variable was the 1/lambda square, so that is 4. So here in this case, the standard variation is 2. Okay, we're going to use the same setting for all three examples. Now the question is that we're going to load the container with the 100 packages. Okay, so here in this case, N is 100. Then what I'm interested in is that what is the probability that the total 100 packages weight is larger than the 210. Okay, remember each package weight is random. Okay, so there should be some probability. All right. Okay. So how the standardization works? If you remember, the Sn minus n mu divided by the sigma square root of n. Okay. So if we standardize this Sn thing with the Gn, then the Gn is approximately standard normal. Good. So let's do that. So the n is 100. And the mu is 2. Okay. Now the sigma is 2 because the variance is 4. Now square root of 100 n. Okay. So this is the standardized random variable. And we're going to do the same, take a subtraction of the same number divided by the same number. So minus 220. Okay. So this is the 100. And this is 0.5. So this probability is equal to this probability. Now the next, from the central limit theorem, this is approximated by the distribution of standard normal, CCDF. Okay? And that is equal to the 1 minus the CDF of the standard normal. That is the probability of the z is less than or equal to 0.5. And using the phi function, that is 1 minus phi, 0.5. Okay. Now, in order to compute this, we can look up the normal table. Then it turns out that we get a number. Okay. But I will not go to the detailed number, but you can do that. But this is how it works. Okay. So this is an example where n and a is given, then we would like to know the real probability p. Okay, now let's look at this case. Suppose that the n and b is given, then we're going to look at the a. Same setting. N package, n is 100 packages. Then we would like to know a, where the a can correspond to roughly the capacity, right? Because we're going to load with 100 packages, and then we're interested in the whole weight of the 100 packages larger than a. So a can be a capacity. Now I want to maintain this probability is roughly 0.05. Okay, so I would like to restrict the overload probability is just 5%, like 0.05. So how can we do that? So we need to know the capacity of the bag in some sense. Okay, so again we do the standardization, and this is a minus 220. Okay, now this is again the z 100, and this is a minus 200 divided by 20. This should be maintained by the 1.05, and this probability is equal to the 1 over probability of the CDF, because this is a CCDF, and that is the z is the standard normal, so 1 minus 5 a minus 200 divided by 20. Okay, so again we can go to the look at the lookup table of that. This should be the 0.95, because this is 1 minus. So what is the value in the table such that this phi function is 0.95? It turns out that if you search that, then it turns out that 1.645. That's why a is 232.9. So we need the capacity of the large bag of the about like 233 in order to satisfy the overload probability is maintained by just 0.05. And that's the example where the n and b is given, then we are figuring out the a. Finally, we can give a and b and then figure out the number of packages. Same setting. Okay. Okay, so the question is how large n should be so that the probability of Sn is larger than the capacity 210 is maintained at the 0.05. All right, how many packages? Okay, so what we can do is that we standardize it, but we don't know what is n. So Sn minus 2n, because again the Zn is Sn minus n mu sigma square root of n. Okay, all right, so 2n, because the mu is 2 and sigma is 2 and the square root of n, and that's we do the same thing like minus and divide by the same 2 square root of n. All right, and that is roughly, as we saw in the previous slides, 1 minus 5 function of this guy, because this is roughly the standard normal. Now this should be maintained by the 0.05. Okay, so this guy should be the 1.645, and if we solve this the quadratic equation, then we get n is 89. So we just can take like 89 packages in order to maintain the 0.05 overload probability with the capacity of 210. Okay, so I've showed the 3 examples of using the central limit theorem, and essentially the central limit theorem, when we practically use this central limit theorem, is that the standardize the random variable, and that is roughly is equal to the standard normal.